What up? This is 2005 mechanics question number 1. Ball of mass m is thrown vertically upward with initial speed of v naught. It experiences a force of air resistance given by F equals negative kV, where k is a positive constant. Positive direction for all vector quantities is upward. Express algebraic answers in terms of m, k, and v naught. Does the magnitude of the acceleration of the ball increase, decrease, or remain the same as the ball moves upward? So if we check out like a force diagram, right? If we look at the ball's motion upward, so our velocity is this way. There are two forces that are exerted on the ball as it's rising. Right? And let's make this a little bit bigger so I can draw those. We have gravity, which is going downward and is going to be a constant value. And we have the drag force or air resistance force, whatever you want to call it. Call it just FR, right? That is also pointing downward. So right now they're a vector sum, right? They're adding together. As the ball goes up, right, its speed is going to decrease, which means this resistive force is also going to decrease, which means our net force downward, where we had a lot, right, at the beginning when our speed was very fast, we had a big resistive force. As it goes up, it's going to slow down. We're going to get a smaller resistive force, which means our acceleration, because it's based on the total amount of force that we have here, is going to decrease. As the ball rises, V decreases, which makes air resistance which was in the same direction as gravity. Decrease. So a smaller net force will mean or a decreasing net force equals a decreasing acceleration, right? As our net force decreases, our acceleration will also decrease. Right, but do not solve a differential equation for the instantaneous speed of the ball in terms of time t as the ball moves upward. So you can kind of do this as the ball moves upward. So in terms of forces, or you kind of have to do this in terms of forces, right? So differential equation, instantaneous speed of the ball in terms of t time. So we have two forces, right? Fg and our resistive force, Fr. And if we sum the forces, right, sum of the forces in the y direction, we'll get negative Fg minus F. The minus sign right here is going to take care of the minus sign right there. So I want to be careful that I don't put two minus signs there. But Fr is going to equal the mass of the ball, m, times the ball's acceleration. And so if we look here, right, gravitational force is going to be m times g, which is a fundamental constant, so that's fine, minus k times v equals m times, which this again is that capital M for the mass of the ball, times a, and acceleration is dv dt. And now we have a differential equation that is set up to be solved for velocity. We could separate out the variables if we wanted to, I guess. Right, if we wanted to move dv to the same side as dv, we could do that, but I don't think we have to do that. It says we don't have to solve it, so we can just leave it like that. But if I wanted to move v over, I would divide v to the other, or sorry, we'd probably have to add mg and then divide by v, it would be hard. It would be difficult to separate those out. I guess that's why they tell you not to worry about solving it, because it'd be a little bit difficult to solve those, to separate the dv and the dt to get it so you can solve for dv. Determine the terminal speed of the ball as it moves downward. So when the ball is moving back downward, right, as velocity is this way, that switches the direction of the resistive force. So resistive force is up, gravitational force is down. We will have terminal speed when these two are equal. So, or right, because we won't have acceleration anymore. Some of the forces, the F net, will be 0 because we have no acceleration. So resistive force minus gravitational force is going to be equal to 0. Resistive force is kv equals fg. This terminal velocity is going to be equal to m times g divided by k. There is our terminal velocity, mg, divided by k. Does it take longer for the ball to rise to its maximum height or fall from its maximum height back to the height from which it was thrown? So it takes longer to fall. Why does it take longer to fall? As our ball travels, right, that resistive force, the air resistance, takes away mechanical energy. Which means the total speed of the ball, right, is going to decrease as we go along, right? The average speed has to decrease. So the resistive force is taking away energy, which means velocity, the average velocity on the way up is greater than the average velocity on the way down, but the distance is the same. Right, distances are equal. So if the way up has a greater average velocity than the way down because air resistance is taking away mechanical energy the whole time, then the time for the downward travel must be bigger or larger, however you want to say it. So it does the upward motion quicker than it does the downward motion because we're constantly losing energy to mechanical energy or to those resistive forces. On the axis below, sketch a graph of the velocity versus time, or of velocity versus time for the upward and downward parts of the ball's flight, where TF is the time at which the ball returns to the height from which it was thrown. So they've kind of led us to a couple different things here that we should make a note of. First, we know the initial velocity, right? The initial velocity, it told us, was V naught. So we know the starting velocity. We also know the terminal velocity, right? However, how fast it's going to be when it is ending. And there's two things that we know about, or there's something that we know about this too. The terminal velocity has to be less than the initial velocity. Because we've lost energy the whole time, the terminal velocity would be less than the initial velocity. What else do we know? We know that the time to go up is shorter than the time to go down. So we can't have our graph cross right in the middle because that would say that the velocity, the time of the velocity going upward will be the same as the time of velocity going downward. So we can't have that. So our velocity has to cross on this side somewhere. And I think that's really it. But let's just pick out a point. Maybe our velocity crosses right here. So we go down. And then we get this asymptote, right, as we reach the terminal velocity. Now, I probably could have made that a little bit less dramatic right? We could have made it more of like a, sorry, it's hard to draw with this. It's hard to draw nice, flat, straight lines. But I could have made it a little bit less dramatic where we go like, ugh, I can't do it. I actually can't do it. I thought I could do it. I can't do it. Right, where we come down here and it's more of a gradual kind of, I made it worse. Whatever. Those are like literally parallel. You guys kind of understand what I'm saying, right? It could be more gradual. It doesn't have to be that dramatic shift that I made. Maybe more like this. That's kind of what I was trying to do. But yeah, so we have this situation where we asymptote at the terminal velocity, and then we end up back in the hand at TF. So there we have our graph there. And that's it. All right, there's problem number 1.